The universe has an edge, not a wall, not a fence, something far stranger. We can see exactly 93 billion light years across. And here's the strange part. The universe is only 13.8 billion years old, which means the edge of everything we can observe shouldn't even exist at the distance where we find it. But it does. And what lies beyond it might be the single most unsettling question in all of science. Because the answer isn't just that we don't know. The answer is that we may never be allowed to know. Let's start with something deceptively simple. Look up on a clear night and you see stars. Thousands of them. Each one a sun, some far larger than our own, scattered across the Milky Way like embers from an old fire. But every single point of light you see with your naked eye belongs to our galaxy alone. And our galaxy is just one island of stars among an estimated 2 trillion galaxies in the observable universe. That word, observable, is doing enormous work in that sentence, and most people skip right past it. Because the observable universe is not the universe. It's just the part we're allowed to see. And the boundary between what we can see and what we can't is one of the most fascinating constructs in all of physics. It's called the cosmic light horizon. And reaching it, truly understanding what it means, requires us to rethink what edges, boundaries, and distance actually are when space itself is the thing that's moving. Here's the first piece of the puzzle. Light travels fast, roughly 300,000 kilometers every single second. In the vacuum of space, nothing with mass can travel faster. This is not a suggestion or an engineering limitation. It is woven into the geometry of reality itself. Einstein showed us that the speed of light is the cosmic speed limit, and every experiment we've ever conducted has confirmed it. So when we look at the night sky, we're not seeing the universe as it is right now. We're seeing it as it was. The light from our nearest star, Proxima Centauri, left its surface about 4 years ago. The light from the Andromeda galaxy departed 2.5 million years before you were born. And the oldest light we can detect, the cosmic microwave background, has been traveling for 13.8 billion years. It was released when the universe was only about 380,000 years old, when the first atoms formed and space became transparent to light for the very first time. That ancient glow surrounds us in every direction. It is the farthest thing we can see. And in a sense, it is the wall. But it's a strange wall. Because when that light was emitted, the matter that released it was only about 42 million light years away from the point that would one day become us. Today, that same matter, carried away by the expansion of space, is roughly 46,005 billion light years away. The light took 13.8 billion years to reach us, but the thing that emitted it has been receding the entire time. Space itself has been stretching, like the surface of a balloon inflating, and every point on that surface moves away from every other point. This is why the observable universe is 93 billion light years across, even though nothing has been traveling faster than light. The light obeyed the speed limit, but the road it was traveling on grew longer during the trip. Now sit with that idea for a moment, because it means the edge of the observable universe is not a place we could ever visit. It's not a location you could point a spacecraft toward and fly to. It's a horizon in the deepest sense of the word. Just as a sailor on the ocean sees a horizon that moves as they move, our cosmic horizon is defined by our position and the age of the universe. Someone standing on a planet near the edge of our observable universe would have their own observable universe, centered on them, stretching 46.5 billion light years in every direction. And parts of their sky would contain galaxies that we will never, under any circumstances, see from Earth. Not because they don't exist, but because their light hasn't had enough time to reach us, and due to the accelerating expansion of space, it never will. This is where the idea starts to become genuinely strange. Because the expansion of the universe is not slowing down. For the first several billion years, scientists expected it would. Gravity pulls matter together, so the mutual attraction of all the mass in the cosmos should have been gradually decelerating the expansion, like a ball thrown upward that slowly loses speed before falling back down. In 1998, 2 independent teams of astronomers set out to measure exactly how much the expansion was slowing. They used Type Ia supernovae, a particular kind of stellar explosion that always reaches roughly the same peak brightness, as cosmic mile markers. By measuring how bright these supernovae appeared versus how bright they should have been at their measured distances, The teams could calculate the rate of expansion at different points in cosmic history, and what they found stunned the world. The expansion wasn't slowing down at all. It was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been if gravity were the only force at play. Something was pushing the universe apart, and it was winning. That something was given a name: dark energy. Not because scientists understood it, but precisely because they didn't. The word dark in physics almost always means unknown. Dark energy makes up roughly 68% of the total energy content of the universe. And after more than 2 decades of study, we still don't know what it is. We know what it does. It creates a kind of anti-gravity on cosmic scales, a repulsive pressure embedded in the fabric of space itself. One leading hypothesis is that dark energy is simply a property of empty space, that the vacuum of the universe carries an intrinsic energy that causes it to expand. And as it expands, more vacuum is created, which carries more energy, which drives further expansion. This idea is related to what Einstein called the cosmological constant, a term he originally introduced into his equations to keep the universe static and later called his greatest blunder. It turned out he may have been right for the wrong reasons. But here's what dark energy means for the edge of space. Because the expansion is accelerating, our observable universe is actually shrinking in a meaningful sense. Not in physical size, as it will always grow as more ancient light reaches us, but in terms of how much of the universe we will ever be able to contact or observe. Right now, light from galaxies beyond a certain distance is being carried away from us faster than it can travel toward us. This distance is called the cosmic event horizon, and it sits at roughly 16 billion light-years away in terms of proper distance today. Any galaxy currently beyond that threshold is lost to us forever. Every photon it emits from this moment forward will never arrive at Earth. The galaxy will continue to exist. Stars will be born and die within it. Planets may orbit those stars, and perhaps life may contemplate its own sky from within them. But to us, that galaxy will fade, redshift into invisibility, and vanish from our universe as though it never existed. If this sounds like a kind of cosmic loneliness, that's because it is. Given enough time, trillions of years from now, nearly every galaxy outside our local group will have crossed beyond the event horizon. The night sky of the far, far future will contain only the merged remnant of the Milky Way and Andromeda, surrounded by an empty void. Any civilization arising in that distant era would look out at the sky and see nothing. They would have no evidence that the universe was ever anything more than a single galaxy adrift in infinite darkness. The cosmic microwave background would have redshifted beyond detectability. The expansion history of the universe would have erased its own evidence. They would live in a universe that had, for all practical purposes, hidden its own past. So what is actually beyond the edge? What exists past the cosmic light horizon, past the event horizon, past the last photon that will ever reach us? The honest answer is that we have strong theoretical reasons to believe more universe exists out there, possibly an enormous amount more, but we cannot observe it, and we may never directly confirm it. Everything beyond the edge is, in the strictest empirical sense, outside of science's reach. But that hasn't stopped cosmologists from trying to figure out what's there. And the models they've built range from the plausible to the genuinely mind-bending. The most conservative and widely accepted view is straightforward. The universe beyond the observable edge is more of the same. More galaxies, more stars, more planets, governed by the same physics, arranged in similar large-scale structures, filaments, walls, and voids of galaxy clusters stretching in every direction. This view is supported by a principle called the cosmological principle, which states that on sufficiently large scales, the universe is homogeneous and isotropic. It looks roughly the same everywhere and in every direction. The cosmic microwave background supports this beautifully. Its temperature is uniform to 1 part in 100,000 across the entire sky. Whatever direction we look, the early universe looked nearly identical. This is strong evidence that the universe doesn't suddenly change character just beyond the edge of what we can see. There's no reason to expect a wall, a boundary, or a fundamentally different region of space waiting just past the horizon. The most likely scenario is simply more universe, stretching far beyond our ability to see it. But how much more? This is where estimates get truly humbling. Some calculations, based on the observed flatness of space, how parallel lines behave over cosmic distances, suggests the total universe could be at least 250 times larger than the observable universe in diameter. Others place the lower bound even higher. And some models of cosmic inflation, the theory that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang, suggests the total universe could be so unimaginably vast that the observable universe is to the whole as a single atom is to the entire observable universe. Let that comparison settle in. Everything we've ever seen, every galaxy, every photon of the cosmic microwave background, every quasar at the edge of observation, all of it could be an almost imperceptibly small patch of a structure so large that we lack the language to describe it. And inflation brings even stranger possibilities to the table. In many versions of inflationary theory, the process that caused our universe's rapid expansion didn't happen just once. It may be happening continuously in different regions of a much larger structure. This is the concept behind eternal inflation. In this framework, our universe is like a single bubble that nucleated within a vast, ever-expanding foam. Other bubbles, other universes, form constantly, each one potentially with different physical constants, different particle masses, different forces. Some of these bubble universes might have 3 spatial dimensions like ours. Others might have more. Some might allow the formation of atoms in chemistry. Others might not. This is the landscape of the multiverse, and while it remains speculative, it arises naturally from some of our best-tested theories of fundamental physics. If the multiverse is real, then beyond the edge of space doesn't just mean more galaxies. It means entirely different universes, possibly with entirely different rules, separated from us not by distance in the conventional sense, but by the inflationary expansion of space between the bubbles. You could travel in a straight line forever at the speed of light and never reach the border of another bubble universe because the space between you is expanding far too fast. These other universes would be causally disconnected from ours in the most absolute way physics allows. But let's pull back from the speculative edge and ask a different question, one that sounds simple but contains an abyss of complexity. Does the universe have a shape? Because if it does, that shape determines what beyond the edge even means. General relativity tells us that mass and energy curve the fabric of spacetime. On a cosmic scale, the total density of all the matter and energy in the universe determines its overall geometry. If the density is above a critical value, the universe curves back on itself like the surface of a sphere. In such a universe, if you traveled far enough in one direction, you'd eventually return to your starting point, like circumnavigating the Earth. This is called a closed universe, and it would mean there is no edge at all. The universe would be finite in volume but without a boundary, just as the surface of a sphere has no edge. If the density is below the critical value, space curves the other way, like a saddle, and extends infinitely. This is an open universe. And if the density is exactly at the critical value, the universe is flat. Euclidean geometry holds on the largest scales, and it also extends infinitely. Our best measurements, primarily from the Planck satellite's observations of the cosmic microwave background, tell us that the universe is flat to within a margin of less than 0.5%. This means the universe is either exactly flat or very, very close to it. And if it is truly flat, it is most likely infinite. Not just big, not just unimaginably large, infinite. And an infinite universe is where language and intuition begin to break down entirely. Because in an infinite universe governed by a finite number of possible quantum states, every possible configuration of matter must eventually repeat. Given enough space, the exact arrangement of atoms that makes up your body, sitting in this exact position, watching this exact video must be duplicated somewhere. Not as a metaphor, as a mathematical certainty. This idea is sometimes called a Boltzmann brain argument or a doppelganger universe. And while it sounds like science fiction, it follows directly from the mathematics of infinity and quantum mechanics. In an infinite universe, not only is everything possible, everything is inevitable. But we need to be careful here. There is a critical difference between what mathematics permits and what we can verify. The entire enterprise of science rests on observation, measurement, and falsifiability. And anything beyond the observable universe by definition cannot be observed. This places the question of what lies beyond the edge in a strange philosophical category. It is a question that physics can model and reason about, but it may never be a question that physics can answer with certainty. Some philosophers of science argue that the question itself is meaningless, that asking what exists beyond all possible observation is not a scientific question at all, but a metaphysical one. Others argue that if our best-tested theories predict something beyond the horizon, we should take those predictions seriously even if we can't directly verify them. Just as we take seriously the prediction that the interior of a black hole contains a singularity, even though no one can observe one. There is one more layer to this question, and it may be the most profound of all. We've been talking about the edge of the observable universe as though it were a limitation of distance and time. But there may be a deeper limitation at work. Our understanding of the universe is built on general relativity and quantum mechanics, two theories that are spectacularly successful within their own domains, but fundamentally incompatible with each other. General relativity describes gravity and the large-scale structure of spacetime. Quantum mechanics describes the behavior of particles and forces at the smallest scales. At the boundary conditions of the universe, the first instant of the Big Bang, the interior of black holes, the ultimate fate of cosmic expansion, these two theories collide and neither one can give us a complete answer. We need a theory of quantum gravity to go further, and despite decades of brilliant effort, we don't have one yet. This means that our picture of what lies beyond the edge is painted with incomplete brushes. String theory, loop quantum gravity, causal set theory, but these are all attempts to unify our understanding, and each one paints a different picture of what the deepest structure of reality might look like. In some versions of string theory, our entire three-dimensional universe is a membrane, a brain, floating in a higher dimensional space called the bulk. Other brains might float nearby, each one an entire universe, separated from us by a direction we cannot point in because it extends along a dimension we cannot perceive. If this is true, beyond the edge of space might not mean farther away in any direction we know. It might mean adjacent, in a direction that our three-dimensional minds cannot visualize, separated by a gap smaller than an atom in a dimension we have no sense organ to detect. This is where the question transforms from astronomy into something closer to philosophy. What does it mean for something to exist if it can never be observed, measured, or interacted with? Is an unobservable universe still real? Does real even apply to things that have no causal connection to our experience? These are not questions that telescopes or particle accelerators can answer. They live at the intersection of physics, philosophy, and the fundamental limits of human knowledge. And yet, the remarkable thing is how much we have figured out. A century ago, we didn't know other galaxies existed. 50 years ago, we didn't know the cosmic microwave background was the afterglow of the Big Bang. 25 years ago, we didn't know the expansion of the universe was accelerating. Each of these discoveries pushed the edge of our knowledge further outward and revealed a universe stranger, larger, and more beautiful than anyone had imagined. The history of cosmology is a history of horizons receding, of edges that turned out not to be edges at all, but doorways into deeper understanding. So what is beyond the edge of space? Perhaps more universe, stretching outward in every direction, filled with galaxies and stars and worlds we will never see. Perhaps other universes entirely, born from the same inflationary process that created ours. Each one a closed cosmos with its own physics and its own history. Perhaps higher dimensions, folded and hidden, containing structures we lack the mathematics to describe. Perhaps something so fundamentally unlike anything we know that we don't yet have the concepts to think about it, let alone the words to name it. What we know for certain is this: the edge of the observable universe is not the edge of reality. It is the edge of our current ability to see. And every generation of scientists has pushed that edge a little further, revealing layers of the cosmos that the previous generation couldn't have dreamed of. The universe has been under no obligation to be small enough for us to understand, and yet, piece by piece, we've understood more of it than any reasonable person could have predicted. The edge of space is not a wall. It's a question. And the fact that we can ask it, that we can sit on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, and genuinely wonder what lies beyond the farthest horizon, may be the most extraordinary thing about us. The universe may not owe us answers, but it seems to keep giving us better questions. And perhaps in the end, that is enough.